Okay, first of all, if you go to the home page in Moodle, or I'll keep calling this Moodle, it's Canvas, sorry. Jeez, we've been working with, we have not worked with Moodle for over a year, but I'm still saying it. And you go down here, I mean, you could see like a rough schedule, and you will notice that we're pretty much on it for the most part. And that the first exam is slated to take place a week from tomorrow. And that will cover the first 8 sections of Chapter 8. Okay? So I just wanted to put that on your radar. We'll probably have some time to do a little bit of review, although it does help that everything is recorded. So, I mean, if you're rough in some area, you could go back and watch it. Hopefully that'll help you out a little bit. Are there any questions before we get started here? Questions? The other thing I'll say is we'll have another quiz on Thursday, and in all likelihood that will cover section 4 and 5 of Chapter 8. Okay, so that'll give you a few days to get your feet under you with respect to trig substitution and partial fractions. Can someone tell me when the next section of WebAssign is due? I don't remember. Okay, and which one is that? 084. Okay. Okay. So, thank you. Any other questions? Well, hang on a second here. Let's talk about L'Hopital's rule. Okay. Now, what's interesting about L'Hopital's rule is it typically in the calc sequence comes fairly early on during limits. Now, this book tries to delay the presentation of L'Hopital's rule as long as possible, because it turns out that L'Hopital's rule often becomes a crutch that you do not need, but and it sort of destroys intuition about how limits are behaving. But when you start getting into improper integrals, more complicated integrals, it becomes a needful tool to have in our back pockets. Now, I should say, historically, this has been called L'Hopital's rule. But that's not because L'Hopital discovered it, right? Turns out that back in the day, the academicians used to have benefactors that would kind of pay them to do their research, okay? And L'Hopital was just such a, his name was, it was Marquis de L'Hopital. And one of his benefactors was one of the Bernoulli brothers. You've probably heard of the Bernoullis before. There were lots of them, and they were all pretty prolific as it pertains to mathematics, physics, what have you. And this rule that is called L'Hopital's rule actually came from one of the Bernoullis. And L'Hopital asked, hey, can I put my name on that? And they were like, sure. I have my name on lots of other things. So this was a gifted result due to one of the Bernoulli brothers that L'Hopital got his name attached to. It's one of the most famous rules that we apply in calculus, though. Okay, so that's an interesting little tidbit. I don't know that L'Hopital didn't contribute anything to the discussion, but seriously, if you're working with one of the Bernoulli brothers, they probably did the bulk of the work. There's no question. Okay. So here's kind of the outline. We're going to talk about indeterminate forms for limits, okay? This is kind of paving the way for Chapter 9, where limits are going to be front and center once again. I want to say that in calculus, there's really only 2 ideas. one of them is limits, and the other one is estimation, okay? And sometimes some combination of those two are used. Now you might remember horrendous things like Riemann sums to approximate integrals, but in the end, that was an estimate, was it not? And then to make it precise, what did you do? Took a limit of Riemann sums. Do you remember that? Okay. So two ideas in all of calculus: limits and estimation. Okay. If you neglect one or the other, you're going to be in trouble. If you think that one is unimportant or that one is more important than the other, you're going to be in trouble. You need to be prolific at limit manipulation and estimation, also kind of using that alongside of it. Okay, so that's my strong exhortation to you as it pertains to calculus. I just lost my notes here just a second. All right. So we're going to look at indeterminate forms, which are things where that show up when you're computing limits, where you kind of say, I don't know what to do. I can't tell. And so you have to resort to kind of manipulating the thing, putting it into a different form so that you then can understand what to do. And oftentimes you try to manipulate it into a form that will involve the proper usage of L'Hopital's rule. Okay? Now, one mistake that students tend to make is once they get L'Hopital's rule into their cognition, they start using it for everything. And that is an incorrect way to proceed too, okay? There is a certain type of limit that L'Hopital's rule is designed to handle, okay? So you can't just use it on anything, okay? So let's do some examples on limits, and we'll kind of think about these things together. So first of all, there are a few limits that, at least in this calc sequence, you were asked to memorize. And then you were asked, or then you were actually shown why they happen to be true using things like geometry and the squeeze theorem. Do you remember the squeeze theorem? And one of those was this limit. Limit as x goes to 0 of sine x over x. Okay, now that is of the form, okay, and now that is of the form, if you tried to plug in 0, you're like in trouble, you know what I'm saying? So it's like of the form 0 over 0, and of course none of you would say the zeros cancel, and therefore the limit is 1. That isn't, okay, that is the right answer, but it is the wrong type of thinking. In fact, that is just abominable, okay? You cannot do that, okay? It is of the form 0 over 0. Now, it turns out that you can use the squeeze theorem along with geometry to show very clearly that this limit is, in fact, 1, but it is not because the zeros canceled, excuse me, okay? Okay? A second one that you were asked to memorize is this one, okay? Limit as x goes to 0 of, depending on how you saw this, it was, 1 minus cosine of x over x, okay? Once again, this is of the form 0 over 0. And this time, if you were so bold and yet foolish at the same time, to cancel the zeros and conclude that this limit is 1, you would be wrong. So what does this limit end up being? Do you know? 0. Okay? You end up getting 0 in this case. That was another one you were asked to memorize. So these are all limits that you had to kind of memorize at some point if you took the calc sequence here. Okay? Limit x goes to 0. The third one is limit x. Oh, by the way, that second one you can verify based on the first limit by doing some clever algebraic manipulation. multiplying top and bottom by 1 plus cosine of x, for instance, would do the trick, okay? You would end up with, if you multiply top and bottom by 1 plus cosine of x, you would get 1 minus cosine squared, which is sine squared, yes? We'd have an x downstairs, and you have a 1 plus cosine of x, and you could break the thing up and actually use the first limit to compute the second, okay? I won't go through all of that, but just know that this limit is 0. Okay, the last one is limit as x goes to 0 of e to the x minus 1 over x. Anybody know what that is? And by the way, this is once again of the form 0 over 0, yes? This one actually is 1. Okay? But you can see that the reason this 0 over 0 right here, 0 over 0 is kind of an interesting thing. And you can see that if the thing is of the form 0 over 0, you don't always get 1. You get different things sometimes. So that's why in calculus, we say that this is an indeterminate form. That is, there's something deeper that we would have to explore in order to figure out what that limit actually is. Okay? No. All three of these happen to be of that special form 0 over 0. Okay, but there are lots of other indeterminate forms, which we will look at together. Okay, any questions on this? These were the big three that we memorized. If you took the class from me, which some of you may or may not have, I don't think any of you in here took the class from me, but I used geometry, like graphical geometry, to establish all three of these. Okay? I just kind of used graphical geometry to establish all three of these together with the squeeze theorem. So again, the squeeze theorem is a way of estimating something. You squeeze it between two things. Estimate, and then you kind of take the limit, and it turns out you squeeze that thing to this particular value. The first and third one I used geometry. The second one we just used algebra, like I was talking about. Okay? Any questions on this? Right? Okay, let's talk about indeterminate forms. 0 over 0, which is the form we just dealt with. What is going on? Can someone like push the power button on that? Can you reach above you and push the power button on that? Or is it that green thing in the middle? Yeah, kind of. Maybe it'll turn on here. We'll see. I don't know what's going on with these things. It just kind of is on sometimes and off other times. So 0 over 0 was the form we encountered all three times on those examples we just did. But another indeterminate form is infinity over infinity. So like if you have one thing going to infinity and another thing going to infinity, what would be completely obnoxious is if you did what? Yeah. Totally incorrect. And here's an example of why. So watch this. What if I had something like the limit as x goes to infinity of pi x over 3x? What does that equal? What happens to the x's in this case? Yeah, they cancel. And what do we end up getting as the limit? Yeah, pi over 3. Right? And you notice that this was originally of the form infinity over infinity. You see what I'm saying? Like pi x goes to infinity, but so does 3x as x goes to infinity. Yeah? And yet we get the constant pi over 3 as the answer. Interesting. Okay. And in fact, I could make infinity over infinity, that form in the limit, be anything that I want by just choosing constants appropriately. I could even make it be infinity, all right? So infinity over infinity, there's something deeper that we have to explore to figure out what's going on. Sometimes the top will be growing faster than the bottom. Sometimes the bottom will be growing faster than the top. Sometimes it will be growing at the same rate so that you'll get a constant as the limit. But what does L'Hopital's rule say? says this: if the limit as x goes to a of f of x over g of x has the form oops, I didn't write that correctly, has the form 0 over 0 or infinity over infinity. And by the way, you could have pluses and minuses in here as well, okay? Okay. Then the following is true. The limit as x goes to a of f of x over g of x is equal to the limit as x goes to a of f prime of x over g prime of x, okay? And one thing I will point out here is that the derivatives, so notice that we need f prime and g prime to exist, of course. Okay, so that's kind of a necessary condition for us to even use L'Hopital's rule at all. We need to be able to take the derivatives and plug in x equal to a into the derivatives, okay? But I would remind you sternly that the only time you can apply L'Hopital's rule is if you happen to be in the indeterminate form 0 over 0 or infinity over infinity. There are lots of other indeterminate forms. But there are times where you can actually manipulate something into one of these two forms and then use L'Hopital's rule, as we'll see here pretty soon, okay? All right, any questions on that before we start applying this thing? So if it's of the form 0 over 0 or infinity over infinity, then the limit of that ratio is equal to the limit of the derivatives of the ratio with derivatives replacing the original functions, okay? That's it. Any questions on that before we start doing some examples? Yes.
So you're saying that we shouldn't use this as a different kind of indeterminate form?
Until you've manipulated it into the form 0 over 0 or infinity over infinity, you can't apply L'Hopital's rule. But there are indeterminate forms that we will look at that can be manipulated into this. You'll see by either like taking logarithms or doing some kind of finagling like that. Okay? Yes, sir. No, we didn't prove it, but we could. It would just involve, like, do you remember the mean value theorem? It involves the mean value theorem. Basically, what it involves is a function is well approximated by its tangent line. If you're really close to the point you're computing that tangent line at. In this case, what are we getting really close to when we're computing this limit? What are we getting close to? The number a. And what we're basically doing is we're kind of thinking about the tangent line at a to these functions as opposed to the functions themselves. And it turns out, we're looking at the slope there now, f prime of x at it. Does that make sense? Because that's what the slope of the tangent line would actually be. It's not hard to prove it, but that's essentially how you do it. Okay, other questions? Good questions. All right, let's do an example. So, hey, why not look at this guy? Limit as x goes to 0 of sine x over x. You know what that is already, right? But what's the form of this thing? 0 over 0. So we can apply L'Hopital's rule, right? So this would be equal to the limit as x goes to 0 of cosine of x over x, because we take the derivative of top and bottom. Oh, oops. Cosine of x over, 1. And what happens if you plug 0 into cosine? 1, which we knew. What about this one? Limit as x goes to 0 of 1 minus cosine of x over x. Okay, and once again, 0 over 0, so we can apply L'Hopital's rule. This would be the limit as x goes to 0 of, what's the derivative of the top? Well, actually, it's just sine because there's a negative sign there, right? So it's just sine of x over 1. Plug in 0 and you get 0. What about the limit as x goes to 0 of e to the x minus 1 over x? Well, once again, 0 over 0, L'Hopital's rule. This is limit as x goes to 0 of and we plug in x equal to 0 and we get 1. Okay? Make sense? Let's do something more interesting. Watch this. What about the limit as x goes to 0 of, not x goes to 0. Oops. Let me write it like this. That's supposed to be an infinity symbol. Do you know what I'm saying? X goes to infinity of 1 plus 1 over x raised to the x. Yeah? What about that? What's the base going to? 1. What's the power going to? Infinity. But here's the thing. It may not at first glance appear that those two things are at odds with one another. But they are. Why? Why would they be at odds with one another? So the power is getting huge, right? The base is not quite at 1. So what's the power trying to do with that base? Drag it off to infinity. Do you know what I'm saying? But the base is saying, no. I want to stay close to 1. So those two things are at odds with one another. Therefore, this is an indeterminate form. And it's the indeterminate form 1 to the infinity. Now you might just say, good grief, why isn't that just 1? But just think about it. What that means is the base is going to 1, but the power is trying to drag this thing off to infinity. Does that make sense? And by the way, if I happen to be on the other side of 1, like if I was a fraction between 0 and 1, you know, then that thing is trying to go to 1, but the power, what would the power be doing to a fraction between, it would be trying to shrink it to 0. Do you know what I'm saying? Because if you raise a fraction between 0 and 1 to a big power, it's going to try to shrink it. So those two things would be at odds with one another, whether I was on the right side of 0 or on the left side of, or on the right side of 1 or on the left side of 1. Okay? So can I apply L'Hopital's rule to this as it stands? No. So what am I going to do? Well, it would be nice if I could pull that power down. How do I pull a power down? Use logarithms, yes? But I can't just like a maniac take logarithms unless I make sure to undo that. What's the thing that undoes a logarithm? Exponential, yeah? So watch this. What you can write here is you can say, well, it's the limit as x goes to infinity of e to the logarithm of 1 plus 1 over x to the x. And what's that going to allow me to be able to do with this x that's sitting right here? I can put it right here, okay? And I can do all the limit stuff in the power now, and the exponential is just kind of coming along for the ride. So this is like e, and now I'm just going to say it's the limit as x goes to infinity of what? I mean, I can, look, the limit only applies to that thing inside of the exponential function anyways, right? The base is just sitting there. It's just the exponential. So it's going to be limit as x goes to infinity of x times the logarithm of what? 1 plus 1 over x. Exactly right. What's the form of this? Let's think about this together. What is the form of this? What happens if I let x go to infinity? Well, the x part goes to infinity. The logarithm of 1 plus 1 over x, what is that going to? Logarithm of 1. So what's that? So this is like infinity times 0. You might say to yourself, well, what the heck? Isn't that just 0? Well, I disagree. I think infinity wins. You know what I'm saying? Like that just means that one thing is trying to go to 0 while the other thing is trying to go to infinity. Does that make sense? That's another indeterminate form. 1 to the infinity is indeterminate form. Infinity times 0 is an indeterminate form. And we'll have a list of these pretty soon. I just wanted to do an example where you saw a couple of them show up. What can I do to turn this into the form we want? Yes. It's because we're taking limits. Yes. So one of them is getting close to 0, but the other thing is getting massive. I don't even know what that would be, my friend. Right? What would that be? What would win? Would it be 0? I don't know. I mean, actually multiplying by infinity, I don't even know what that means. Does that make sense? Like, well, so it's like, okay, one thing could be getting close to 0, but the other thing might be trillions. And it might make it big anyways. Does that make sense? Okay. So what can we do with this thing that's in the power? What do you guys think? Yeah. Exactly right. You can put it as natural log of 1 plus 1 over x. And then you basically just do a little trick, and instead of seeing as x, invert that below the logarithm thing, yes? This is going to be over 1 over x, yeah? Now what's the form of this thing? What's the form of that if I let x go to infinity? The top goes to logarithm of 1, which is 0. The bottom goes to 0. Ah. So what can I apply? L'Hopital. Okay. This is going to be E. So now it's of the form 0 over 0. So I'm invoking L'Hopital's rule. It's going to be E to the limit as x goes to infinity. Now I have to remember, all right, okay, I draw a giant fraction symbol. And I say to myself, okay, the derivative of the logarithm is 1 over the thing. Yes? Okay, so it's 1 over 1 plus 1 over x times the derivative of what's inside. What's the derivative of 1 over x? Derivative of 1 over x. Negative x to the negative 2. You think of it as x to the minus 1. It's going to be negative x to the negative 2. Let me write that as just negative 1 over x squared. And what's the derivative of the bottom? Same thing, negative 1 over x squared. Know what I mean? So what happens to the negative 1 over x squareds? They cancel. Oh, wait, not like that. What did I just do? I just erased it. Okay, negative 1 over x squared. Okay, this and this cancel. And now what happens if you let x go to infinity? What does 1 over 1 plus 1 over x go to as x goes to infinity? 1. It's like e to the 1 over 1 plus 0. Does that make sense? Which is just e. So interestingly, look at this. Look what we've proved. This limit equals what? E. Yeah? That weird limit is equal to E, and that's actually a fairly famous limit. In fact, that might have been the fourth one that you should have memorized from Calc 1 or something. Yeah. The limit as x goes to infinity of 1 plus 1 over x all to the x, that goes to E. It's a very, very famous limit. Okay? So this is an example of how one can actually turn an indeterminate form into the L'Hopital form by utilizing exponentials and logarithms to our advantage. Okay? Questions on that? Any questions? Yes?
I don't know if I should ask this question, but why doesn't order of operations resolve like the full and be
Order of operations.
so like with the limit of x going to infinity, why doesn't the fact that you're getting the one like you do the function 1 plus 1 over infinity first?
Okay, so to be specific, if x was like 37 trillion, okay, then what you're saying is 1 plus 1 over 37 trillion is some number that's slightly bigger than 1, yeah? But then I'm supposed to raise that to the 37 trillion power. So what do you mean by order of operations?
So wouldn't the one wouldn't the number close to 1 just result like you taking the power of 1, right? You raising the power, you raising the number 1 close to 1 to 37 trillion.
Yeah.
Wouldn't that just make it 37 trillion? Like
Make it 37 trillion.
1 times 37 trillion is 37 trillion.
But it's not times 37 trillion. You would be raising that number 1 point whatever.
Yeah.
You would be raising that number to the 37 trillion power.
So yeah, so since you're raising it, wouldn't it? Right, so I'm not thinking multiplication, but if you were to raise it to the power, wouldn't it just be like? Wouldn't it just be raised to the power? Why is it fighting?
Well, okay, try raising 1 point. I mean, try doing that exact thing. That base is trying to get really close to 1 and therefore stay close to 1. But then raising the thing to the 37 trillion power, what does that do to it? It drags it back off upwards. Does that make sense? Which is at odds with where the base is trying to go. Yeah. Okay. Like
When you move the limit up to be just to the power it was raised to and pulled out the E, is that like similar to like integral rules, how it's like E is a constant?
Well, it has to do with the fact that the exponential function is continuous. Like it doesn't matter, like is the base going anywhere? Once I've kind of put the exponential function in there and the logarithm, is the base moving at all? What's the only thing that was moving? the power itself. Does that make sense? So the limit, all of the limit stuff is happening in the power anyways. So you can just pull it up there. Does that make sense? The bottom's not going anywhere. The base isn't going anywhere. Okay, good questions. Other questions? All right. That's a cool limit. By the way, if instead of a 1 right here, here's a little thing you can go think about at Chuck's. If instead of a 1 right here, what if it was like a 2? What if that was a 2? Okay. Well, you can kind of follow that around. That would mean that this would be a 2. Yeah. That would mean that this would be a 2. Right. This would be a, right. Okay. This would be a 2. Where else would I have a 2? Oh, right here. This would be a 2. Yeah. Where else would I have a 2? Wouldn't this be a 2 right here? But that would still be a 1 down there. And what would happen? Wouldn't I have a remnant 2 dangling around? Do you see that? There would be a 2 right here. And so what would the answer be? Do you see that? Amazing. What do you think is going to happen in general with that number that happens to be in the numerator of the x thing inside of that power? It's going to be e raised to whatever that thing is, I promise. If you go think about that at Chuck's for a while, you'll convince yourself that that's true. Does that make sense? Okay? You do the exact same thing that we just did. Look, I mean, it doesn't even matter. I could have put any number a right there and it would have happened for sure. Okay? All right. That's an awesome limit. Let's talk about indeterminate forms. Here are the indeterminate forms. Didn't we just encounter 2 of these in that last problem? We encountered this guy right here, 1 to the infinity. What's the other one that we encountered? 0 times infinity. Okay. We already know that 0 over 0 and infinity over infinity, those are the L'Hopital ones, right? So the L'Hopital indeterminate forms are those 2 right there. But I'm telling you, there's a few other ones. Infinity minus infinity, which is not 0, excuse me. Okay. One of those infinities might be much bigger than the other one. Okay, or might be going to infinity much faster than the other one. Okay, so that could be hugely positive or hugely negative. 0 to the 0, why are those at odds with one another? Yeah, so think about it. In this case, the base is trying to get teensy and go to 0, right? But what's the power trying to do? Take it to 1. Do you see that those 2 things are at odds? One thing is trying to go to 0. The other thing is trying to go to 1. Trying to force the base, force the whole quantity to go to 1. Those are at odds. Conflict. Yeah? Indeterminate form you should think of as conflict. Okay? What about infinity to the 0? That one's more obviously indeterminate. Infinity to the 0. What is raising something to the 0 trying to do? But the base is trying to go off to infinity. Clearly, those are in massive conflict with one another. Okay? If you get one of those expressions, it's oftentimes by way of algebra, factoring things out, using exponentials and logarithms to get it into the L'Hopital form, like we just did in that last example. Okay? Let's do some more examples. Here's one. And I want you to work on this, at your table. How about this? Limit as x goes to 2. Okay, what does that mean if I put that little minus sign like that? What am I doing? From the left, x goes to 2 from the left, which it doesn't matter. In L'Hopital's rule, it doesn't matter if it's going from the left or the right or just going there. But you'll see why I need that here in this case, okay? 4 minus x squared all over x minus 2. Okay, why do I, first of all, before you guys start working on this, why do I need to go to 2 from the left in this case? Yeah, look, if I plugged in a number bigger than 2, 4 minus x squared would be negative. Does that make sense? So you end up with something negative under the square root. Okay? So think about this with your comrades in arms around you, okay? Okay. I hate to interrupt some awesome discussion, but I want to finish this the next 5 minutes. What did you discover was happening if you just started blindly doing stuff? What happened?
You kind of got stuck after you did L'Hopital's rule the first time.
What happened? It looked like you had to just keep doing it and it just kept getting more and more complicated?
You couldn't keep doing it because it was then 2 over 0. So you had to.
Well, if you got 2 over 0, that's sort of exciting. That's not indeterminate. It just depends on what side of 0 you're on.
Mhm.
So if you got the form 2 over 0, tell me how you did that.
Well, okay, so
Did you just fly L'Hopital's rule straight up?
because it was 0 over 0, and
So you probably initially thought of this as 4 minus x squared
which is,
to the 1/2.
yes, which would be
Okay.
0 to the 1/2 over 2 minus 2, which would also be 0.
Okay, so hang on. So the limit x goes to 2 from the left. Now this is of the form 0 over 0, so we apply L'Hopital. So you get what? Limit, so you got 1/2
times negative 2x.
well, 4 minus x squared to the negative 1/2
Yeah,
times negative 2x all over what?
all over 1.
All over 1. Okay, which is what? This is going to be, so the 2's kind of cancel, do they not? Okay, and so you end up with the limit as x goes to 2 from the left of negative x over what?
Over square root of 4 minus x squared.
Now, let me ask you something, and this is kind of funny notation, but I think it'll be helpful. The top just goes to negative 2, doesn't it? So this is like going to be negative 2 over what? It's over 0, but 0 how? Is it like going to 0 through positive numbers or negative numbers? Of course, positive numbers is square root. Does that make sense? So I'm fine with you writing this. This is basically negative 2 over 0, but going to 0 through positive numbers. Now you tell me, if you take something close to negative 2 and you divide it by some teensy positive number, what are you going to get? You're going to get a massively negative number. Does that make sense? Take something close to negative 2 and divide it by something teensy and positive, you're going to get a huge negative number. So what is this limit? Negative infinity. Negative infinity. All right? Cool. We'll look at some more examples next time, and we'll start applying this in the context of integrals.